workshop is about PCBs. So just a little background. So a printed circuit board, if you guys are not familiar with it, is used to connect various electronic components together. It uses SMD, surface mount devices, and through-hole technology, and communicates with each other via electrical traces. So why do we use PCBs? PCBs are used because they're easily designed, they're small. Okay, they're small and lightweight, making it ideal for complex systems, and a single board can be used to perform multiple functions. So this is actually our PCB design from for this year for a low voltage system. As you can see, there are multiple components on it, although there are some components missing from the actual manufactured PCB. You can see there are various components on there, and they all kind of work together. And here are some more examples of more complex PCBs. As you can see, they can vary in complexity and how many components can actually go on it. And then there's some more simple ones as well. So what does a PCB consist of? So PCBs are made out of non-conductive material with copper layers in between. And obviously, depending on the PCB design and functionality, it can have a single layer or it can have multiple layers. So what are the layers? So there are four main layers. There's a substrate layer, which is made of fiberglass and kind of gives PCBs a structure. There is a copper layer, which allows electrical signals to flow throughout the board. There's a solder mask layer, which protects the copper from other metals and gives PCB its green color. PCBs can also be different colors. Green is not the only color. And then there's a silk screen layer, which is used to label components onto the board. So here's a little picture kind of giving a breakdown of how the layers are arranged.
So there's different types of software you can use to design PCBs. So the most popular ones are Altium, KiCad, and Eagle. They're all really great free options, but by far the best one is Altium. And that's just because it has a very large database of components from a lot of online stores such as DigiKey and Mouser. And then it also has a lot of features and extensions within the software itself. So you can perform different signal integrity simulations, such as looking at overshoot and undershoot. You could make crosstalk simulation and could even input different termination schemes to see how your schematic will behave. You could also perform transient analysis, which is something that's more commonly seen in software such as LTSpice or Circuits Lab. And you could even create a power distribution network where you can pinpoint all the hot zones on your PCB. And overall, it's very sleek, it's comprehensible, and it's a top tool in the industry. So this is kind of an overview of the PCB design process. You first start with an idea. What task do you want to achieve, or what goal are you aiming for? You head into the research phase. So what components do you need? Do you need any type of protective circuitry, or how would you implement it? What type of power sources do you need? Do you need it to be DC or AC? So once you have that done, you head more into your schematic and you draw it. And that's when you can simulate it with different types of software, such as Virtuoso, SysCapture, even LTSpice. During this phase, you should be taking note of the expected behavior and trying to understand what you're actually designing. Next, you should focus on prototyping, and that should be more on the semi-permanent board testing. I'm pretty sure you guys are familiar with breadboards, and that's really ideal because you can adjust different components and wiring and really understand what's going on. Some useful tools during this phase would also be using multimeters, power sources, oscilloscopes, and function generators if you need an oscillating function. And during this phase, you need to think about whether your testing actually, your real life testing actually matches your simulations. Are the waveforms correct? Is the output voltage correct? What about the current? And then you could head straight into designing. You can use any of the software that we've mentioned before, or any other ones that are more accessible to you. The next phase is manufacturing. There's some criteria that we can give you pointers on, and we'll talk about that later in the presentation. After that, you head into assembly and testing. This is the fun part. You solder all your SMDs and through-hole technology. You connect your power supplies, you strip and crimp your wires, and then you check if your design actually works. You optimize and fix things. Most times PCBs don't work on the first run, so you need to set time aside to see what's happening with your design, read through the data sheets, and try to understand what's going on. You might have to reiterate this phase and make a couple PCBs before you could actually get your final product.
Okay, so what are some things that you should consider when designing a PCB? So first of all, you want to think about the board size. Obviously, that's dependent on your design and what will go on it. So for example, this year's PCB is approximately 5 by 7 inches, which is approximately the size of a calculator. Compared to previous year's designs, I believe last year, the year before, the PCB was a lot bigger. I think it was by like 13 by 7 inches. So we were able to reduce it significantly in size, but still maintain the same amount of components and even add more circuitry like protective circuits. You also want to look at the number of components and materials going onto your board. So this is when the data sheets come in. You want to look into the data sheet for each component to ensure it meets your design specifications. For example, the size, the current and voltage ratings, etc. Also, the orientation of components is really important. So you want to put similar components together to make soldering easier. So like your SMDs and THT components should be separated so they don't get in the way of each other when you are soldering. Also, there is the power and ground plane. So planes should be centered appropriately on the PCB so that power is evenly distributed between the components and does not result in interference, because this can obviously affect the functionality of the board. So similar to this picture, that's kind of how you want to arrange the power plane and the ground plane.
All right, some other pretty big considerations is signal integrity and thermal optimization. But for the first one, it's signal integrity, and that just refers to ensuring a quality transmission of electric signals. So you could have some problems with signal integrities wherever you have vias, wherever you have more than 2 signals branching, where you have a signal plane that splits, any high-speed signals, or mismatched impedances. So this could also result in a lot of problems. So for example, if you have mismatched impedances, you can have things such as ringing and distortions. If you have any reflections, you'll have overshoot and undershoot. And if you have high-speed signals or clocks, you'll get crosstalk, which is essentially the interference of electromagnetic fields, and that does not allow for a clean signal. Some sample solutions for this would be using a ground plane instead of a common return path, matching your impedances, and then specifically for high-speed signals and crosstalks, it would be good to a good rule of thumb would be to separate your signals 2 times the trace width. And then if you have a multi-layer design, it's a good consideration to have your traces perpendicular. So if you have them horizontal on the top layer, on the bottom layer, they should be vertical. And then termination schemes. So the bottom right is an example of a parallel Schottky diode. And during this, the 2 diodes are going to be used to clamp any overshoot and undershoot. And so that would reduce essentially the problems that we could be facing. So that's just one example. And then the picture above, you could see that if we have a square function, a pulse wave, I should say, you ideally want to avoid all the overshoot and ringing going on, because that's not what your signal actually is. Next slide, please. Okay. And so the other issue is thermal efficiency. And this is really important because if you have a component that's operating at a temperature that it's not designed to operate in, it's going to reduce the efficiency of your component and your overall design. It could damage your PCB board and even burn your components. So different ways you could analyze the power distribution of your circuit is by using ANSYS SI wave, or simply just popping open like an Excel sheet and just seeing which components are too hot. So some considerations for your design would be, for example, the components that dissipate the most power would be ideal to keep around the edge of the board. Or another thing is just to consider what's outside of your board as well. Is your PCB going to be near something that's going to dissipate a lot of power, and how would that affect your circuit type of thing? So those are other tips to keep in mind. And maybe even consider using heat sinks or just replacing components with lower power dissipation. The last thing is adhering to IPC standards, and that the IPC standards are electronic industry adopted standards for designing, PCB manufacturing, and electronic assembly. And these are basically guidelines that could ensure a safe implementation of a PCB. And in the bottom is actually an analysis of a sample board through SI wave on ANSYS. All right, so now the tips for the PCB manufacturing. So some key things to consider when picking a manufacturer is one, quality. So are the holes going to be drilled correctly? Is there minimum board warping? Are they going to perform a bare board test for you? And batch size. Are you making a small project and you'll need about 5 PCBs, or are you going to manufacture these PCBs and need about like 100 or 200? Timing. Do you have a deadline, or can you wait? The cost. What is your budget? How much money are you willing to invest in this project? And then just extra services. Extra services can include layout review, where engineers could actually contact you about your design and could point out any possible problems. Does that matter to you? And just lastly, will the manufacturer meet your design constraints? Can they drill your hole sizes? Can they meet your tolerances? Will they print the layer number that you have? And just also material type. Will it be RoHS compliant? Do you care if it's a lead or lead-free board? There's some 3 manufacturers here, and probably the best one we've worked with so far is JLC PCB, because they have a small, sizable batch starting at 5 boards. They're cheap and they're pretty quick. It's 1.5 to 2 weeks. PCBWay is also a really good option. It's affordable. And then a high-end example is Sierra Circuits. And they just provide a bunch of extra services that could ensure like a functioning board, which is why they're usually more expensive. And usually they start around, for our PCB, their starting price was $150. And for a JLC PCB, the total price was $50. So that gives you like a comparison of the different types of services they provide.
All right, so what are the steps to designing a PCB? There are 6 main steps. Obviously, there are details in between. I'll just read through the steps and then we'll give you guys a live demo. So the first is you want to lay out your schematic. This can be done in Altium. You want to choose your components and lay them all out so you can see what's being connected to what. Create schematic symbols in the schematic library. The schematic library is kind of used to just see how many components you have in your circuit. And it kind of helps you keep track of everything. You want to create footprint symbols in the footprint library. This will help you when laying out the components onto the PCB. The 4th step is to actually create the PCB layout. 5th is to create the bill of materials, otherwise known as the BOM. And then 6 is the Gerber files, which are used to send to the manufacturer.
Okay, so that was pretty much that was an introduction, but now we're going to jump into today's project. So today we're going to be following the sample motion sensor buzzer. And so we're going to be using a PIR sensor, 2 resistors, an LED, a BJT, a buzzer, and a DC source. Next slide, please. So this is a sample layout of what it would be on a breadboard. And this is going to be our schematic layout for today. And Safia will build it for us. This is the PCB layout. And then with the ground plane. And another good thing to do is, in terms of documentation, is to create a BOM. So this could be created either like on a Google Sheets if you want, or it could also be created through Altium as well. But if you use the Google one, it's really helpful because you could add all the links directly in the items and you could have access to the data sheets instantly. And it also gives you a good idea of how much money you're spending on a project. This is without shipping, of course, but still pretty affordable project. Yeah, that's it.
Yeah, so let's get started on the project. So I already have Altium installed. We'll give you guys a link at the end of the presentation for you guys to install it yourselves. So this is kind of what Altium looks like. I'm going to have the BOM to my left so that I can easily click on the components and see what the requirements are for each component. So in Altium, to start a new project, it's pretty standard. You go to File, click on Project. I'm just going to call it Workshop. And then Create. Bear with me, my Wi-Fi might make things a little slow. Okay, so we have the project here. So currently there are no documents added. So I want to first start off my PCB by making a schematic layout. So I'm going to add new to project, and I'm going to click on schematic. So this is what the schematic sheet looks like. You can change the size of the sheet. You can add a title, but just for the sake of time, I'm just going to leave it the way it is. And so I'm going to start off by going into my BOM and seeing what I need to place on my schematic. So I already have all of them up. So first is the LED. So this is the LED. It gives you like a manufacturer part number. It tells you if it's a through hole or SMD component, tells you the current rating and the voltage rating. You can also click on technical data sheet, and that'll take you to this page, which will give you the dimensions, which I will get back to in a little bit. So there are two ways to search for components in Altium. You can go into panels and you can click on components, and you can search for components that way. Yeah, so you can search in components this way. I like to use the manufacturer part search, which is another way of doing it. So for instance, I'm gonna copy this and I'm gonna see if I can find it in the manufacturer part search. Oops. Okay. So they do have the component, but they don't have a symbol for it. So the reason I like using manufacturer part search is because it gives you a price, it tells you if it's in stock, and it tells you which company has it. So that's a really nice feature about the manufacturer part search in Altium. So what I'm going to do is I'm just going to search in LED because it's just a standard LED. We can there's more flexibility with that. So all the options that are coming up right now are SMD components, but we don't want SMD components for this design. We want through hole. So there's a filter option here that you can click on, and it'll allow you to filter the LEDs. So I want through hole, and based on the specs right here, I want the forward voltage drop to be about 3.2 volts, and that's something you can choose here too. So there's 3.2 volts. Okay, so here you can see it's by, they have this LED by Worth Electronic. It has 3.2 volts, 30 milliamps. That's pretty close to what we have here on this website. And you can see how much it is and if it's in stock. So that's a really nice feature. So I just need one for my design. So I'm going to right click and I'm going to push place. And so see, I'm sharing my screen and I'm on Zoom, so my computer is bugging out a little. Let me see if I can just place it. Okay, so I placed it. So then I'm going to do the same. I'm just going to move this over. So I'm going to do the same thing for the two resistors. So this is a resistor. We need a 470 ohm resistor and a 220 ohm resistor. So I'm going to search for it the same way. What's nice in manufacturer part search is that you can actually choose resistors as an option. So let me get rid of these filters. So I'm going to go to passive components. And then just going to type in resistors. I'm also going to filter so that I get a through hole component. So I'm just going to click on axial. The value doesn't really matter in this case because most through-hole resistors have the same dimensions. So anyone will do. This one seems fine. So I'm just going to click on it and then I'm going to place this as well. Going to place 2. Okay. Just going to leave those. And then, so the next component that I want is the buzzer. So I'm going to try to see if they have this buzzer when I look for it under manufacturer part search. I have a feeling it's probably not going to be there. But let's just give it a shot. So they have it, but they don't have the symbol. So what I'm just going to do is I'm just going to look up a piezo buzzer. So we know that it has to be 8 volts, 15 volts, either of those. Voltage, I guess, doesn't really matter in this case either. So I'm just going to choose this one and I'm going to place it. And then the next component we have, oh, another thing I wanted to mention is that in the BOM, we have like the 9-volt battery, the battery clips, and the female header. Those are external components, and so that's why we don't need to add that to our PCB. So the next thing I want to look into is the PIR sensor. So I'm going to also look for this in Altium and see if they have it. Same case, they don't. So I'm going to look for that. So I'm just going to search up just a generic one. So the range is from 3 volts to 6 volts. This is also 3 volts to 6 volts. So I'm just going to choose that. I'm going to place it. Another thing you want to keep in mind if you can't find the exact component. So for example, this has 3 inputs. You want to make sure that the component that you're choosing from Altium also has 3 inputs, just so it's similar and you don't get like confused in your design. So I'm just going to rearrange some components, and then the last component that we need is the NPN transistor. This is a pretty common part, so I'm expecting it to be in Altium. Yeah, so 45 volts is what we're expecting. The maximum voltage here, it says 45 volts. So this is perfect. This is exactly what we're looking for. So I'm just going to place that as well. So those are all the components I need for my circuit. So now the next step is to wire everything. So based on our breadboard and the diagram that Beverly made, just going to go back to it real quick. So we can see that the resistor, oh, let me back up a little bit. Before I start wiring, I want to label my components so I know which one is what. So we have a 220 ohm resistor. So what I'm going to do is I'm going to, instead of having the manufacturer part number here, because that can get confusing at times, I'm just going to label it 220. And then I'm also going to label the resistors. So I have R1, and I'm going to do the same for this one. 470 ohms. Label this R2. I also want to label it so that if someone who's not familiar with the circuit looks at it, they'll know what each component is. This is pretty standard. I'm hoping everyone knows what a transistor is. But yeah, so this is what it looked like. So based on the breadboard, we can see that the resistor R1 is connected to VDD. Another thing I forgot to mention is you can flip the orientation of your component just by clicking the space bar. So by flipping it like this, I can connect the circuit a little bit better. Okay, so now I'm ready to start wiring. Shortcut to wiring is just Control W. So I'm going to 120 ohm resistor needs to be connected to VDD, and it's connected to the base of the transistor. And then the 470 ohm resistor is connected to the LED. And then the LED is connected to the collector of the transistor. And then this is just connected to ground and 9 volts. Another thing you want to pay attention to is the polarity of your components. So for example, the buzzer doesn't really have a polarity. So where you put 9 volts, where you put ground doesn't really matter. So I'm going to start placing ground. So based on the breadboard, we can see that the emitter is connected to the negative side of the battery. So I'm going to ground that. I'm also going to ground the sensor. And I'm going to ground the resistor here. And then to add 9 volts, I'm also going to click on ground, but I'm going to change it so that I'm going to change the value and the schematic so that it's you can easily tell that it's 9 volts. So I'm going to label it 9 volts, and then instead of a power ground, I'm going to change that into a bar. And then I'm going to do the same for the buzzer. So one's going to be ground, one's going to be the source. And then change that to the bar. There you go. There is your schematic. So once you're done with your schematic, you obviously want to save. Don't want to lose all your work. So the next thing you want to do is you want to make your schematic library. As I mentioned before, schematic library is just there to kind of keep track of all the components you're using in your circuit. So you want to go right click on your project, add new to project, and you want to add a schematic library. Adding a schematic library is really straightforward. You just go back into your schematic and you just copy your schematic and you paste it into the library. So just good old Control C and then Control V, and then it pops up right away. So I'm going to do that with the rest of the components. If there is a component that you have multiple of, so like for example, the resistors, obviously you just need one in the library. One more. Okay, so that's all the components. This extra one, I'm just going to delete. So there you go. You have all 5 components in your schematic library. So the next step is to create a PCB library. So this is where you're going to have all the footprints for your PCB. So you want to save that as well. Save the project. So I'm going to add new to project, and I'm going to add a PCB library. So there are several ways to make a footprint. Make my screen a little bit bigger. So there are several ways to make a footprint, depending on which component you have, either SMDs or through hole. It'll obviously the way you make your footprints will vary. So there are a couple wizards on Altium that allows you to make footprints pretty easily. So as Beverly was mentioning earlier, there's IPC compliant footprints. And these are good for like SMD components because SMD components can be very small and there are a lot of details that you don't want to miss. And so you want to make sure that your dimensions and everything are properly made. So just to give you guys an example of what components can be made through the IPC compliant footprint wizard, and they're usually like SMD components. So these are like examples of what the components would look like. So you could use that. I'm not going to use that today because everything we're using is through hole. You could also use the footprint wizard. Yeah, footprint wizard, which is what I'm going to do for the resistors. So I'm going to show you guys how to make 1 or 2 footprints because it gets pretty repetitive. And so I'm going to start off with the resistor. So before you do that, you want to go into the data sheet for your component. So here's the data sheet for the resistor. So I'm going to click on resistors. Select the unit. I'm going to use millimeters because that's what it says in the data sheet, that it's in millimeters. So next, you have an option to choose if it's surface mount or if it's through hole. It's through hole in our case. So the pad size is, the hole is 0.6 millimeters. That should be fine for our design. You get used to reading data sheets. 0.6 should be fine, but because the diameter is 0.6, I'm just going to increase it to like 0.62 based on the tolerance that they give on the data sheet. If you guys can see, it says plus 0.02. So I'll just do 0.62 just to be safe. And I'm going to click next. Pad distance, because it's a through hole component, there's more flexibility. Because they're just wires, you can always like play around with it. And if it's not a perfect fit on the PCB, you can kind of like force it to go in the way you want it to go in. So 15.2 millimeters seems like a very large distance between the pads. So the length of the actual resistor, without looking at the wires, is 6.8 millimeters. So maybe the distance between the pads should be like, I'm just going to make a guesstimate and say 8 millimeters. Height and width of the outline. This is just the silk screen that we talked about earlier that goes on top. It kind of just gives an outline of where the component would be on the PCB. The dimensions of this doesn't really matter because you can adjust it. And then I'm just going to call it resistors, or I'll just call it res. And it's done. So this obviously looks a little strange. You can mess around with it. So you can like pull it and you can adjust it to however you want it to be. Just for the sake of time, I'm not going to really play around with this. So if you click tab, it kind of highlights the entire silk screen. You can just delete it. So these are your footprints. So on the PCB, you're going to have 2 holes, and that's where the resistor would go. And so you can also, this is a 2D layout. You can look at a 3D layout. So this kind of shows you, what it would look like on a PCB. And so I actually made the footprints for the other designs a couple days ago that I can show you guys. But the process is the same. You just look at the dimensions based on the data sheet. You can also, another thing I forgot to mention is that if you don't want to use a footprint wizard, you can easily make footprints for through hole components just by right-clicking, going to place, and then clicking on pad. So just to show you guys, when you click on pad, you can click anywhere and then a pad will pop up. And then you can click on it and then you can adjust the hole size right here. And you can adjust the X and Y dimensions, and then you can adjust the hole size based on the component. And then you can change the name of the designator so that it's easier to identify on the PCB. And then you just basically play around with play around with it till you get the dimensions that you want. So I made it for the buzzer, the resistors, the PIR sensor. So as you can see, I added the proper designators, output VDD ground. And then I also made one for the transistor. So collector, base, emitter. So that's how you make the footprints. And then Beverly will show you guys how to make the rest.
So let me share my screen.
Sharing.
All right, so can everyone see my screen?
Yep.
All right, so now the remaining steps would be to lay the PCB and then just create output files. So in order to import the design from the schematic, you have two different ways. So if you open the schematic design right here, you could click on design and click update PCB schematic. I already had updated it into the current design, so it's going to be there. Another way you could do it is look at, open the PCB schematic document tab and then import changes, and it should open the same window. So essentially when you have this window, you're going to have, you should have checks here. If you have any X's, that means that you need to go back and look at the errors that it's going to be talking about. So some errors could be that you'll have mismatched pad numbers, or you could just have some connections that are basically free and not connected to anything, and that will cause errors. So as long as you get all green checks, you'll validate that little check and you just execute it and you're done. So, oh, sorry, it's green here just because I didn't take off the green room, sorry. So you have your components here, and you could start by essentially choosing how big you want your board. So you press 1 on the keyboard. And then when you hit design, you could redefine the board shape, you could edit the board shape, or you could modify the board shape. But we're going to edit it because it's a little big. We could make it smaller, like that. We can make it different shapes, of course. Oops. So it doesn't, it could be whatever you want it to be, but we'll just keep it simple. And a little square or a little rectangle as best as we can. But yeah, so after you get your board shape, you press 2 and then you go into the design essentially. And this is when you start laying out all your component parts. So these are essentially the footprints that Safia had made. What we're going to do now is untangle the rat's nest. I don't know if you could see all these light gray lines, that's essentially all the connections and all the nets between the components. And so we're going to fix these optimally so we could route things. You could change the orientation just the same way as we did in the schematic sheet, and that's just by pressing the space bar. So I'm going to put this here and maybe this here. And also it's good to think about the sizing of your components as well. So the MD1 was a big PIR sensor. And so I would want to give that enough space. This here is a buzzer, so maybe I should give it about that much space. And ideally this is going to hang outside the board, which is fine. We'll put this LED here. This is the transistor. And then lastly, the resistors. Reorient it. And that's pretty much it. Okay, so now we're going to place the routes down. So the way you do that, it's the same way as in the schematic document. You put Control W and you get this little cross. So you're going to click on each of the little pads and it's going to highlight where you need to go. So here we could see this ground goes to this pin here on Q1. So you could select on the empty space, and then you'll have this kind of freedom so it doesn't have to look too weird. You could also change the different type of, I guess, curvature of the line by just pressing the spacebar as well. I just prefer this one. So yeah, we just go ahead and connect everything. So now this goes there. Whoops. And then this pin here goes to the MOSFET here. Sorry, the BJT there. And this resistor goes here. This one goes to that net there. And then we could also connect this one here. And lastly, since these are through-hole components, crossing the silk layer isn't really an issue. And lastly, we have this connection, and we could just go ahead and go up across the back. It's a little messy, but you could play around with it. It's not an issue. So another thing you could do here is just that you could change how thick these traces are. And that all depends on, you just double click on it. And that just all depends on how much current you're going to be passing through these traces. So generally for 1 amp, 10 mils is enough. So here we can make it like 100. And it's like really thick, right? But yeah, that will just depend on what your system is going to be carrying. But for a regular MCU 1 amp, that's 10 mils is more than enough. Okay, so after you have that going, you now put in the polygon pour. This is optional, but as we mentioned before, it's pretty useful for minimizing signal integrity issues. So you go ahead, go into place, you click polygon pour, and then you just essentially box your entire region like so, and just click escape. So cool, looks great. So now we have the polygon pour, but we need to assign it to a net. And so we double click on it, and here it says no net. So what we're going to do is click ground, because we want it to be a ground plane. It could also be a power plane if you wish, but for this application, it's just going to be a ground plane. And we're going to repour. You might have to repour it a couple times and repour again. There you go. And you could see it connected with that plane, because if you zoom in, you see that the ground is actually connected to the polygon pour, whereas this one that isn't ground is not connected in that cross form. So yeah, and then the third function you could use is the 3, and that will give you a 3D view of your board. Like so. You hold shift and the right button on your mouse, and you could move it around and see the vias in the back, the traces, or anything that you add. You could also add step models, which you could directly import from something you design on SolidWorks, or maybe some step files that you find online. Or you could actually just create like just a 3D box, and it will also appear in that 3D model. And so you could also look at different layers as well. If you want to look at the entire thing, you just leave it as so. But if you want to focus on a specific layer, maybe we just want to see the top overlay, what we're going to do is we're going to press Shift S. Neat, right? It helps a lot with debugging. And if you just exclusively don't even want to see any gray background, you press Shift S again, and there you go. And just to return it back to normal, you press Shift S one more time, and you're there. Okay, so at this point, you need to check whether your design fits all the constraints. So we're going to go directly into design rule checks under tools. And all of these rules are going to be pre-programmed in the design tab. So we're going to run design rule check. Great, we have no errors. And so whenever you run the design rule check, you're going to get this message tab on the bottom, and it's going to list different errors. So we could make an error. So here's an example. We're going to go to rules, and let's do minimum solder mask clearance. We put that to 2.5 just because we worked with it before, so we know that. But what if we put it to 10? That means that the minimum solder mask, so this green, could only reach the silk mask by 10 millimeters. Anything closer than that is an error. So we're going to hit OK, and we're going to run design rule check again. Look at all these errors. Well, 2. But yeah, so we know that error. So we could also get, since we know the way we would go around debugging it is that we would just look at the tab and see, okay, so this red is the error. We see that the minimum solder mass silver constraint is too close. The minimum is 10 mils, sorry. And then we have 2.63, so that's too close. So we're going to go ahead and go back to the document and change the rules to 2.5 or whatever number is fine, as long as it's smaller. And we're going to run the design rule check again, and we're good. 0 errors. And these are just basically used as a way to keep your IPC standards. So you could input the generic ones that you could find online, and you could stay to those, and then your system will be clear of any short circuits or antennaes. But you could also bend the rules a little bit if you have systems such as this where it's not going to dissipate that much power. So after we have our board, what we're going to do is that the other thing you can do is just validate it, but it's going to be the same thing. So now what we're going to do is going to output these files for manufacturing. The specific files that you need depends on manufacturers. So you would just go online and see what they ask for. So we'll just look at an example for now. So we're going to file, new, and we're going to go to output job file. And you're going to open this page, for example. So we're going to pick our container. Our container is going to be the PDF. I'm just going to call it output 1. And so let's just add a schematic document. So we're going to put documentation outputs, and we're going to put schematic prints, and we're going to print out the project physical document, and we could rename it to whatever we choose. So schematic. If you right click, you could open the page setup, and you could put it to color or to gray. You could change it to either be portrait or landscape, but we'll just keep it landscape and in color. And then for configurations, generally for any schematic properties, you don't need to change anything. And another useful thing to print is the assembly outputs. So we're going to pick the assembly drawings, and we're going to choose the PCB1 PCB doc, basically. That's essentially the board we were looking at. And it's going to be assembly drawings. So we're going to right click, and we're going to configure, and we're going to open up this tab. And this essentially is going to print out the different layers. So we're going to have the top layer, the top overlay, and the multi-layer. And the bottom layer is going to have the bottom layer, bottom overlay, and bottom multi-layer. But if we want to change it, we could just we could just right click, or just double tap. And then we could just add different layers. So let's see, top layer, we can put bottom solder, or okay, we could do bottom solder and put okay, and then it'll appear. Simple as that. And we close it. And we could also adjust the bottom one as we need, but we don't have anything on the bottom, so it's not an issue. And then we just click OK. And then this part is pretty straightforward too. You just click the little arrow, and it's going to print it out there. That's literally it. So then we're just going to generate content. Oh, sorry. So we're going to overwrite the document we already have and generate the content. And there you go. Here is the schematic Safia made, and then the assembly drawings. And we could, oh wait, can you guys see the PCB doc? What is this called? Can you guys see the output, or do you guys still see the Altium screen?
Oh yeah, we can see it, like the PDF.
Yeah, the PDF.
Yeah, we can see it.
Okay, cool. Mm-hmm. So yeah, then pretty much this is the output job. And this is what you submit to manufacturers. So whenever they ask for the Gerber files, you would just submit this, and that's what they ask for. You could submit different things, but it just depends on the manufacturer. But yeah, that's pretty much it.
We'll go back to the slides. Do you want to talk about this?
Yeah. Okay, so that was pretty much a brief overview of how to go through the PCB design process, but here are sort of some supplemental resources for you. So, if you want to do different projects, IEEE at UCI is always, they actually have a project tab and they're always talking about different things. If you want to get ideas or if you just want to ask for help from other students, that's a good place to go. There's a link. And then just some online component stores that you could start looking at is DigiKey and Mouser. And then if you want to learn specifically more about Altium resources, a good YouTube channel to visit is Robert Faranick's channel. He covers everything in so much depth and he does a really good job. And another thing is just referencing the manual as well. They have some really detailed examples of how to use specific features, and they even have a walkthrough of going through a simple PCB design. And then just visiting online forums. So there's Stack Exchange or just Fedival Academy. And then that's the link on the bottom for the student license, if you guys would like to download it.
I just sent the link for the student license.
Thank you.
And I'll also send the link to the Discord if anyone is interested. But yeah, does anyone have any questions?
I had a small question. I know it's kind of simple, but you said overshoot, undershoot. I have like no idea what that is. If you could explain that.
Oh yeah, for sure. So Safia, could you go to the right tab? Just keep on going back until we go to the signal integrity one.
There you go.
Okay, so essentially, when you have reflections, that just means that this entire signal isn't going through. So that means that there's just this excess voltage that's going from the source to that point back and forth until it dissipates as heat. And so what that does essentially is that it adds this extra voltage to your square pulse. And you could see that there with the overshoot, that's the extra ringing, well, sorry, that's the extra voltage that's going on. And you could also get undershoot, which is just excess negative voltage in the opposite direction. So that's pretty much overshoot and undershoot. But the square wave should be the ideal signal, not the excess one.
That makes sense. Yeah, that makes sense.
Any other questions?
I'm just kind of curious, how often is crosstalk actually an issue? Because I feel like it would have to be pretty extreme in order to affect a circuit.
Well, generally crosstalk is an issue if you have high-speed signals. Or if you use clocks, and if you have them too close to each other, they're going to interfere with each other, basically. But if you just have a normal, like a simple circuit, like our example, it shouldn't be an issue. It's specifically for like MCU type communications, I guess.
I see, thank you.
Any more questions?
Do you guys have any examples of like some of the PCBs you guys have designed in the past?
Yeah. So these two PCBs, these two PCBs down here, Beverly and I designed this earlier this year. And so this is for our low voltage system. And so it has an MCU here, which is a Raspberry Pi. We have a DC to DC converter. We have a few relays. We have protective circuitry. We have terminal blocks. We have another MCU here, ESP32. So this is an example of one of our more recent designs. This is our first iteration. We're currently working on our second iteration because after testing it in lab, we realized there were some issues with the first design. And so for the second design, we're not going to have as many relays. So we're not going to use some of the components that we had in the first design. But yeah, this is our current PCB for a low voltage system.
Let's see. No, I also remember you mentioned that this year's PCB is like significantly smaller than last year's. I'm just curious, like what allowed you guys to do that or to reduce the size so significantly?
I think with the previous year's design, we noticed that there was just a lot of space in between components. And so we were able to keep the same amount of components, but we realized like everything could just be fit in more closely and we could just make it more compact. And so it worked out because our pod is also smaller this year. And so we were able to add, I think, a few more components compared to the previous year's design, but still make it smaller.
I see. That's interesting. Thank you.
Yeah, no problem.
I could also share one of the other versions of the PCB that was rejected if you want to see that actually.
Oh yeah, I would actually love to see that.
Okay. Let's see. All right, can you see my screen?
Yeah.
Yeah, so this is one of the original ones that we didn't go with, but as you can see, it's pretty much the same amount of components. It's the 4 relays. We have the DC to DC converter. We have our smart diode, which is our protective circuitry, part of our protective circuitry. And we have like our fuses and we have our connectors in 3D. Whoop, a little lag. See, it looks pretty neat with all the components on and whatnot. So pretty nice.
But there's a lot of space, if you notice, like in this design. So we were able to reduce that for the current design.
Yeah.
Utilize our space a little bit better.
And so these are actually step models. So this MOSFET, we were able to download it from online and then just import it into the design. And then this one here, it was just something that we were able to generate with just the footprint. So it just makes like a rectangular prism and you could just change the color, which is neat as well. But yeah.
To answer Susie's question, why was it rejected? So for this design, we realized the smart diode, Beverly, correct me if I'm wrong, but the reason we didn't stick with the smart diode is because there's a period, so the smart diode doesn't have 100% duty cycle. So there's a period when the pod can turn off and the PCB would basically like the PCB wouldn't turn off in time, or like the pod would turn off and then like power would shut off to the pod. And so we realized we didn't want to use that because that's a risk. And so we completely got rid of the smart diode. And then there's this other component here with like a bunch of little squares. I think that was another converter, but we found out that the ESP32 has its own DC to DC converter built in. And so we were able to eliminate a lot of these components and make things a lot more compact.
Additionally, with the one we actually manufactured, we put 2 MCUs on it and put a lot of terminal blocks.
Yeah.
So that means we would need like more space to put in like a Raspberry Pi, an ESP, and good chunk of little green dudes. we could actually open the PowerPoint to look at it more closely.
I can share.
But yeah, so we have the Raspberry Pi in the upper right, and then the terminal blocks are all the little green connectors. And right next to it is where the ESP goes as well. So we had to put those in as well.
Yep.
Well, I was just gonna ask, if you were gonna improve the current design, what are some things you would make changes to?
So for the second iteration, we realized we don't need as many relays. So we'll have 2 less relays. This right here was for the current sensors, but we also realized we don't need that because that can come through the ESP. The ESP32 can read current. And so we have 2 current sensors that were supposed to go here that are not going to be on there anymore. two less relays. So if there's two less relays, that means two less fuse blocks. And so, yeah, those are some of the components right now that we're thinking of eliminating.
And we're also just going to be doing some rewiring of the terminal blocks because you see all the traces under it makes the connections fixed. So we're just gonna change some around, especially between the two MCUs. Just so like in changing some of the communication, in changing some of the traces between the ESP and the Raspberry Pi, we could eliminate some external components. So just those types of optimizations as well.
Yeah. And also like the way we're going to trace things for the second board, it's going to be a little bit better so we can avoid crosstalk.
Right.
You mentioned earlier. So there's a lot you learn in the debugging process. Yeah.
And also rewiring the crowbar correctly. The crowbar is a protective circuitry we put for over voltage, but when we tested it in lab, it did not work. And in the end, it ended up like frying the breadboard, and it was quite a scene. So, but before that, we were able to figure out the proper implementation. And so we need to also make that correction. So it'll be our second iteration. Hopefully then it'll work.
So which kind of just shows you like the significance of breadboard prototyping, because we fried the breadboard, which is fine. But like we were able to prevent that from happening on PCB.
Ideally, we would have done that before we did the PCB, but things are kind of, we didn't have lab access. And so now we do. And so now we're able to see our different mistakes. So yeah, prototyping, PCB boards, breadboards, all great.
Any other questions?
Bye, Mason. Thank you for coming.
Thank you.
Okay, so I think that's most of the questions. So if you have any other questions, you can email us at ecihyperexite@gmail.com. And yeah, other than that, I think we can end it here. And I hope you all have a good night.